Hey gang, we're back at it. We're continuing on with 6.4. However, today I want you to look at the compressions and stretches that would occur for your sinusoidal functions. So you could have your sine or cos functions. If there is a value in front of them, your a value, just like you would have an a value in front of any other function, it would result in a vertical stretch or compression. Just like before, if the a value is larger than 1, you would have a stretch or compression. And if it is a value between 0 and 1, you would have a vertical compression. You should also realize, and you'll figure it out as you do more questions, that the a value in front, it ends up actually being equal to the amplitude of your sine or cosine functions. So if I wanted to take a quick look at this one over here, and again, I know these graphs are a little bit small. Hopefully you can see them a little bit. But if I have the function y equals 0.75 cos of theta, first of all, the amplitude is 0.75. So we can start off right away by putting that one in. Okay, so the amplitude is 0.75. Okay. Your regular cos function, because this number is between 0 and 1, it will be a vertical compression. So our new graph will be a little bit squishier or more compressed than our original cosine function. So if we were to graph our cosine function, I'm going to change the values here. Let's make this 1, this 2, just so we can see our graph a little bit better. You know, if you're like me, you're getting old and the eyes don't work so well. So here's our cosine function. So we know that cosine starts at 1, and then I went up by 30s on my y-axis. So 1, 0, negative, oops, 0, negative 1, 0, and positive 1. Okay, let me just get rid of the dots we don't need. I kind of put some extra ones in. There we go. Okay, so that would be our basic cosine function. Now, these values, hopefully you don't need me here. I mean, again, I'll always put them in for you if you need them, but you don't really need to put all these extra points once you've got the general idea of what your curves look like. So there's our basic cosine function. So now let's compress this thing by 0.75. Any of the heights or the y values in relation to your axis of symmetry will be compressed by a factor of 0.75. So if this is a whole unit up, take the amplitude of 1 and everything will go down to about 0.75. Okay, so you can compress vertically by 0.75. Again, 0 times 0.75 isn't going to change. 0 times 0.75 is not going to change. And plus 1 times 0.75 will be here. Negative 1 times negative 0.75 would be there. So instead of having the black dotted line, we get this red dotted line. And again, you can try and compress these guys here a little bit if you'd like. Okay, but you can, as long as you've got your main 5 points. And with a paper and pencil, it'll look a lot nicer than my red pen here, okay? But there it is. You've compressed it by a factor of 0.75. So pretty similar to what you did in chapter 1. I want you to look at part B. We are adding in our compression from the things that we did last time on my previous video. So quick refresher, I mean, we are looking at this right here. This 3 would give us an amplitude of 3. It means that our graph, because it's bigger than 1, will be vertically stretched. This number back here is our vertical shift up and down. So this will be shifted up to up. And this one down here, it is negative 120. That means that it is a positive 120. Our actual value is plus 120 because there's a minus in our brackets, which means this will actually have a phase shift in the right direction. So phase shift will be right. I'm just going to put R, okay, but you should put right 120 units, okay, and we've got degrees on our x-axis, so 120 degrees. And then our vertical displacement is up and down. This would be 2 up. Okay. Okay, so we've got all our information without even graphing it, but if you needed your graph first, I like looking at the values to see what's gonna happen, and then I graph it. The graph is just a good way, you can read them straight off the graph. So looking at this, I've got a sine function. I'm gonna start with my sine. Now these ones here, I've gone up to 4. I'm gonna leave those here because I'm gonna need the height because the amplitude my graph has been stretched. So sine starts at 0, at 90 degrees, it's at 1, at 180, it's 0. At 270, it's -1. And at 360, it's 0. Okay, so we've got our main 5 points. Now I have to change all of my transformations. Usually, we do the multiplication before addition subtraction, which means we're going to do any of our compressions and stretches prior to shifting it. So the first thing we're going to do is we're going to make this thing 3 times as tall. So so it's 0, 0. Actually, it's funny. I always love changing my axes first. I think it's so much cleaner and neater. But the proper method is to actually extend it before you shift it around. So 0, 0, these ones, if I multiplied by 3, would not change at all. This one here, it has an amplitude of 1, but my new amplitude is 3. So I'm going to multiply 1 by 3. So there's 1, 2, and 3. And then -1 times 3 is -3. So this distance down here, which was -1, is now going to be -3. So 1, 2, and 3. Okay, so now we've got this curve kind of going this way. I'm just going to see if I can put some other dots in here for you, just so you can see it a little better. There we go. Okay, so that's what your sine graph would look like. But now I have to shift it 120 units to the right and 2 units up. Okay, so I might actually lose a little bit of I might actually lose a little bit of my curve when I graph it. Let's get a different color for these last ones. So take your main 5 points. You are going to move them right 120 degrees and 2 units up. So 120 degrees is here, and 2 units up. So 1, 2. This dot that I'm putting in, I'll make it nice and big, is this guy. Okay. And I'm going to take this, I'm going to take my next one. Actually, maybe we'll do the ones on the x-axis first. I'll take this guy here. I'm going to move him over 120 degrees. So this is 180 plus 120 should bring me to 300 and up 2 units. That's 1 unit, 2 units, okay? Because if you look at the y-axis, my squares go up by a half, so 2 units would be 4 squares up. And then this one, if I brought it over 120 degrees and 2 units up, it would be off of my graph. I'm just going to plot in what I can for now. So I've done this guy, this one, and this one. I need to get this guy up here and this one down here. So I'm going to move this one over 120 degrees. It's at 90. 120 plus 90 is 210. I'm going to be here, and then I'm going to go up 2 units. 1, now 2 is probably about there. It looks like it's just off of my grid. And then when I get down, so that one is up in the right spot. Now when I get this one, it's at 270. If I move it over 120 degrees, I would be at 390, which, yay, is over here. And then I'm going to go up 2 units. So 1, 2. Okay, I am missing some of my graph, but at least I can get the general idea of what is happening. Okay. And I will draw my nice, lovely curve. There's my min, and it'll continue upwards. Okay, yes, you can continue this down because it is a periodic function, and you can follow the pattern all the way to the other side. Okay, let me just put a little arrow on this because our graph would continue, and that is your sine curve that has been moved over 120 degrees and up 2 units. Okay, so that's the easy part for your stretches and compressions. Now we get to work with the horizontal ones, which were a little bit more challenging, and those were new to you this year. So when we're dealing with our trig functions and your horizontal compressions, things kind of get a little bit weird, but if you can keep in your mind that everything inside the brackets is a little bit backwards, and there's one small formula to memorize, you shouldn't be too bad. It will take a little bit of practice, but do your best. So if we have something inside our function, which means it would put it beside our theta or our angle, that's when you would have a horizontal expansion or compression. So multiplying the variable theta for your trig functions by a positive value would affect a horizontal expansion or compression. Don't worry about the negative ones. Those are reflections and it's periodic, so why would we deal with them? Right, because you just slide it over and you'd get the same pattern. So if your K value is between 0 and 1, so now it's a decimal between 0 and 1, because it's inside the brackets, it'll be backwards. Those ones will give you a horizontal expansion or a horizontal stretch. If it is a number larger than 1, then you are going to get a horizontal compression. Those ones will be smaller. Now, how is this K value related to the period of a function? Because remember, the period is the distance of a cycle, and if we're stretching or compressing it, then you are going to be changing the period of your function. So the K value does in fact affect it, and there's a cute little formula for you to memorize. If you play with Desmos, I'm not going to do it, but if you play with Desmos, a plane, there's nothing here, right? Remember in math, we don't like to write things if we don't have to, but you can imagine that there's a 1 here. So the period of our plane cos function is 360 degrees. If you plug y equals cos 2 theta into Desmos, you'll notice that it gets horizontally compressed, okay? It's half as wide or half as long, which means the period is only 180 degrees. If you plug in cos of half a theta or 0.5 theta, that's a number between 0 and 1, it's going to stretch it. So this is a horizontal stretch, and it'll be twice as long. So you should notice there is a connection between the value of K and the period of your function. And this is the formula. 360 degrees divided by K will get the period for the function. Okay, so maybe put a star next to that one and put it somewhere that you won't forget. So we're going to use that idea to draw sine of 3 theta. We'll try with 1 cycle, and if we can get 2 in, we will, and then at the and then we'll state its period. So sine theta. Now I have made this nice and high and really squished in. If you can see the numbers, sine starts at 0, then goes to 1, 0, -1. 0, okay? And you know what the rest of the graph looks like, okay? Now, this is sine 3 theta. So that means because this is a number larger than 1, we will have, it's inside the brackets, it's going to be opposite. This is going to be a horizontal compression by 1/3. So to find our period, or to find the period of the function, we are going to take 360. We're going to divide by our K value, which is 3. This will give us 120. So our new function is going to be 1/3 of the size. Every one of these values is going to horizontally be squished by a factor of 3, right? It's going to be compressed by 3. So let's take my different colored pen. We'll go back to red. Red. So if this was, and I'm just going to look at the main points. If 0 times 3 or divided by 3 is 0, so that one stays here. This one is at 90 degrees, okay? 90 divided by 3 is 30, so this new point is going to be at 30 degrees. This point at 180, 180 divided by 3 is 60. This point is going to be squished at 60. This number is at 270. 270 divided by 3 is 90. So that point is going to be moved over to 90. And then this point right here at 360, 360 divided by 3 is 120. It will be squished all the way to 120. And you have got your new, very squished sine curve. Okay, so let's put 1 cycle in just so we can see it. 1, oh dear, mine look like zigzags. They shouldn't be zigzags. There we go. So that's 1 cycle. And now it asks for 2. So we're going to put the 2nd cycle in. So I'm just going to follow the pattern. Again, try and make it look not like zigzags, but a beautiful curve. And that is the compressed version of sine by a factor of 3. Okay, so you've got your horizontal compressions and stretches. We saw that with cosine, and you've got your vertical compressions and stretches with cosine, and your horizontal, in this case, a compression with sine. Okay, one more thing, and then you're done. It has to do with the period and the phase shift, and it's something that has come up. You ran into it in one of your assignments, and we can combine more of our transformations. So often horizontal expansions and compressions are combined with your horizontal translations. The graphs of these guys are related to basic sine and cosine, but you have some things that are combined together. The one thing that you need to worry about is if there is a K value and a P value, there must be a set of brackets between the K and the theta. Has to. If it is not, and it is written like this, you have to factor in order to make it look like this guy. And you've seen them a couple chapters ago, I think in chapter 4, I believe. So anytime you are curve sketching, if there is a value directly in front of the theta, there must be a bracket between the theta and your K value in order to properly identify your K value. But when you are common factoring your angles, you have to common factor by your P value also. So it has to look like this bottom form right here. So you properly know that in this case, these are the same functions, that here you would be shifting 90 degrees to the right, not 270. So if it is a P value and they write it with a set of brackets, you have to factor it. End of story, there's no debate. Okay, otherwise your question would end up wrong. So now that you know that, let's super fast look at this one here. Come on, pen tool, there we go, in black. So looking at this function, my amplitude, remember that's your A value, that is the height. So my amplitude was typically 1, but with cos, the A value changes our amplitude, so my new amplitude is 2. The phase shift, this would be shifted, I know it says in subtraction, that means it goes to the right. Okay, so this is a positive phase shift of 90 degrees right. Whoop, right. That's why I just put R. And the period, we are going to take 360 degrees and we are going to divide by 3 to give us a period of 120 degrees. Okay, so I'm going to start off with our basic cosine. I don't think I can fit the two functions on, oh, I can fit the two functions on this one. If I can, great. If not, oh well. Okay, so let's start off with our basic function. It would be 1, 0, and -1, and really that's all I can get for now. So let me just start with this one, and this is the way that I do it. I'm almost going to shift my axes over before I start stretching and compressing, but the proper way is to stretch and compress first. So actually, maybe I'll stretch. Okay, so this has a stretch of 2. So instead of having an amplitude of 1, it's going to have an amplitude of 2. So let me get a different color pen so you can see the difference. So that would be up here, right? 1 times 2 is 2, 0 times 2 is 0, that one would stay, and -1 times 2 is -2. So this would be my new cosine. Now, keep in mind the cosine would continue up. So now I have to take care of the 3. This is going to change the period or the length of the cycle. So it is going to be, it is a number larger than 1. It's inside the bracket, so it'll be backwards. So we are going to horizontally compress this. So this one here at 0, I will keep it here for now, but this one I am going to compress by 1/3. So I'm looking at the horizontal distance. If it was at 90, 90 divided by 3 is 30, right? This one's on the y-axis, so its horizontal distance to the y-axis is 0. 0 divided by 3 is still 0. Okay, so I'm looking at this guy. And then this one down here, 180 divided by 3 is 60. Okay, so these are my new points. Okay, this one, and this one. And you can see from the pattern, if I had other points along my grid, my next one would have been actually at 90. My next one would have been up here, right? And that should have given us our beautiful cosine curve. So that's one graph. Now, it does want 2 cycles, but I still have to move it. So let's now translate this thing 90 degrees to the right. So I'm going to take these points, I'm going to move them to the right. So this one, 90 degrees. Now, 1, 2, 3. I've scaled my axes, so 90 degrees is 3 squares. So 1, 2, I think 3 should be there. Okay, 1, 2, 3, 1, 2, 3. Starting here, 1, 2, and 3. And this one up at the top, 1, 2, and 3. Okay, and this, I know they look like V's, they're not, they're cosine curves. So once we've got our one graph, now I'm going to repeat to get the second cycle. So again, just follow the pattern. These ones are just kind of going up and down. Just keep in mind when you're actually connecting your dots that they are curves, okay? So we're gonna start up here and then come down, nice little curve. And you can imagine what this will look like. There we go, okay? And there it is. So we have our cosine curve that has been curve sketched without creating a table of values. It has been vertically compressed by 2, vertically stretched by 2, horizontally compressed by a factor of a third or 3, translated to the right 90 degrees, and we have 2 cycles, and we've listed all of our information to the right. Okay, that's it for today, guys. Tomorrow we're putting everything together. Good luck.